Hello, thank you for coming. So we're going to talk a little bit about cadCAD. cadCAD is actually complex adaptive dynamics computer-aided design. It was built with my team at BlockScience, and we're sort of building out our documentation and tools to make it an open source project. Pretty excited about it, but the sort of open sourcing is something that we're collaborating with the Common Stack to release. This is a general header from the README. It's basically a Python toolkit. It integrates with the Python data science stack, but it's focused on differential games, meaning sort of dynamical systems where people play complex strategies and interact with the system. This is pretty important when we're dealing with these sort of markets and incentives, because there's a lot of things that can happen, and it's not as simple as just saying, hey, there's some equilibrium. But in order to sort of show you something other than a bunch of text, we're going to jump over to a example. This is actually in Jupyter Hub, hosted by the GiveF team. We're running a simulation literally right now, which is of the Common Stack design. This is from the Conviction 3 thing, and this Jupyter notebook contains a bunch of stuff. Here you can see a bunch of initial proposals, initial participants, their preferences over them, and as the system runs, it's going to have more people arrive, new proposals are going to be proposed, and over the course of the simulation, they'll interact with each other, they'll interact with the proposals, some proposals will pass. It's pretty interesting. It takes a little while to run. Maybe we shouldn't have tried to run one live during the demo, sorry. I'll let Jeff sort of, what do you think, Jeff? Do you want to just go back to the GitHub one so that... I'm in the GitHub. Here's the agents that are interacting with each other. This is how people influence each other. These are the proposals and the degree of conflict they have with each other, so we can keep track of sort of whether one passing will make another one less likely to pass. All around, this is an example of a simulation for a project that we are actually designing and testing and iterating, and sort of our methods involve running parameter sweeps and sensitivity tests and failure mode tests and A/B tests over our assumptions. Lots of cool stuff happens. Totally understand this isn't what everyone is going to want to do. We are working on part of packaging up what we learn from designing things into toys and tools that other people can use to sort of set up their own stuff. This example had a bonding curve. We'll kind of key off of that. So the bonding curve component is an interface or a adapter pattern between two economic elements. A lot of people talk about them a lot. We use them in a pretty specific way. Here you can see that our observed data in our simulation sticks to the bonding curve. This is despite the fact that we didn't actually pre-program the price or do anything in particular. We just had variations caused by random processes and behavioral processes, and sort of show that our design respects itself by keeping the price and the supply and the reserve already aligned with each other. What we're going to do, though, is we're going to jump to this sort of JavaScript application that we built based on some of our design work to help people understand the augmented bonding curve design. Help people understand the augmented bonding curve design. So here we have a deterministic relation between supply of tokens and the collateral in the reserve. So the x-axis is collateral, the y-axis is the supply. We aren't actually saying what the exact supply or reserve is going to be. We're saying how they're related to each other. And when we initialize this system, we're going to have a point on this curve, and when it runs and people are participating, it's going to move along this curve, and depending on what people do. But we just know that it stays on this curve, and that tells us something about how the system might evolve. And Jeff's playing with the parameters and sort of setting up. Let's talk about what the parameters are. So we've got, in this case, we're talking about launching a sort of a commons or a DAO that is a sort of like a community center. Its job is to support people in doing something, helps them sort of decide how to, in this case, decide how to do something. It's very general, so it depends on what your community does to figure out what you're going to decide. We still want an interface for capital into this decision-making process, and so we launch a system using, we launch the system by setting the hatch raise percent to funding pool, so some of it's going to go into the reserve to back up the tokens, some of it's going to go directly to the community to spend to do projects. We can set a percentage, we can set a sort of hatch price, which is what we're gonna like initially sell tokens at in order to launch the system. We can set a post-hatch price, which is sort of how the system initializes. It's the slope of the curve at the point where the initialization happens. We have an exit tribute, which is basically saying that when you come in, it's sort of a free flow. When you want to leave, you have to leave some value behind for the community so that people can't just like come in, maybe overly incentivized to try to pump and dump or something. It's very difficult to do that when on your way out of the community, you leave some value behind. And this means that you might speculate, but you're going to speculate long term because you have to think that it's going to rise more than the exit tribute. Otherwise, there's no reason to do this. Sort of a damper on the speculative behavior without saying it's gone completely. And then we have a vesting half-life that also helps prevent the pump and dump. In other words, the people who help initialize the system, they don't actually get to just cash out. There's a period of time, actually first a cliff, where they can't sell any of the initialization tokens, and then a half-life where that sort of becomes available slowly over time, kind of prevents the everyone waits till they're free and drops them and tanks the system. So Jeff's going to show this simulation now, so go ahead and click. So we do a random process generation mixed with some behavior. There's a lot of different ways to generate these curves, but basically people are buying and selling in according to some external signals, and you can see the way the system moves. The support here is the minimum price based on the vesting, so there's no way to tank the system if you can't actually burn all of the tokens. So this is sort of a protection from an initial pump and dump. We want to run it a couple times so we can see that it's sort of not a deterministic simulation. We can get scenarios where we fall below the sort of initialization price. But this is actually part of the reason why we have this spread, right? We want to mitigate the risks of the people who are helping launch this community. And so this means that they paid this, they launched here, the system was protected against falling below that as those tokens were not burnable. Over time, they become burnable, and the community can sort of find a sort of steady state here where eventually the sort of value of what the community is doing sort of balances out with what people are willing to support. And another important thing is that exit tribute means that you're continuing to accumulate capital to spend. One of my favorite things about this design is actually that when you start sort of running on the system, like people are like, oh, this is done, like they don't have any money left, like we're not going to participate in this system anymore. The exit tributes mean that every time somebody sells out, a little bit more money goes in the funding pool. More people sell out, a little more money goes in the funding pool. And then suddenly someone's sitting there who didn't leave in control of all the funds that are left from all of those exits. So there's a kind of a force in the other direction. And this helps keep the system sustainable. It doesn't actually guarantee any particular level. So we're saying, hey, look, we want to find a balance between sort of the labor to maintain this commons and the sort of capital to help, spend on building things. A lot of potential outcomes. And the key here is that while we design something deterministic up here, we actually have non-deterministic behavior, and it's simply processed by the design, and it has some actually predictable dynamics like this pressure away from being burned out. And it has a pressure or protection away from a pump and dump. So there's also some cool properties associated with the exit tribute and the low slippage. It's very unlikely that someone will want to do front running on a system like this, because in order to profit from front running, you would have to basically have a transaction whose slippage was bigger than the exit tribute. Otherwise, you can't profit from like front running somebody. And so a lot of cool stuff. We've been doing a lot of behind-the-scenes design work with cadCAD, and we're doing a lot of sort of forward-looking, how do we take these designs and make them more accessible to people? Any questions? Or?
Yeah, we have time for questions. Maybe a question. So for this simulation, you include the parameters from the ones that you showed us on the top left, right?
Yep.
And do you... It's fine, I guess.
No. So yeah.
So for this simulation, you use the parameters from the top left.
Yep.
Some couple of those, and I guess based on those differences, we see different versions down there, different scenarios. I'm just curious. You showed us some interaction between the nodes, maybe transactions on blockchains, maybe some other activity. Do you include those kind of, or like like simulations from the network interactions into your
So,
simulations?
so it depends. So it sort of depends which simulations you're looking at. So this is sort of pulled up a level for someone to play with. Like this isn't necessarily the design tool for actually designing the thing that you're going to implement. This is for letting someone sort of make parameter choices, and even actually in making parameter choices, we would normally do these types of sensitivity tests with like a much more detailed simulation in the other tool. This is like mostly sort of random process with a little bit of behavior expectation in it. So we have like sort of early big spikes, and then we have sort of responses to this sort of potential gains. And the reason that we see a variety of outcomes here is in part that the processes are partially randomized and partially behavioral. The transactions are actually generated, but they're not like resolved on a blockchain. The transactions are behind the scenes, just like, okay, during this period of week, there was this sequence of transactions, and here's what they actually did to the thing. The statistics for those are in here. So we had our average transaction size and median slippage, where statistics about the effects of specific transactions in this run, but the detail level is still relatively high compared to what we were showing in Conviction 3, which is actually cadCAD. So the Python sort of data science level work is a lot deeper, and we can represent much more complex things and run failure mode tests. It's only as we come to a conclusion that we have a good design there that we might like factor something up to this sort of JavaScript level, where we're making it easier for someone who's not a data scientist to like learn from our work.
So you mentioned the Monte Carlo machine before, right? Can you explain a bit more like what parameters go into this like randomization?
So in this one specifically, or in the like larger simulations? So in this one, there's actually a whole other file. So if you go there, Jeff, can you go to Conviction 3, then go to the top? There's the Python logic 3, the file that has all the logics in it. Yeah, so conviction system logic 3. So that file. Oh, so actually, well, I'll just try to answer. So actually, in these simulations, we try all sorts of different stuff. So there's not actually one, like, oh, this is how people are going to behave, or this is how things are going to involve. We actually parameterize these things. So we have, in that system, we have models of people acting by combining their own private beliefs of the value of the proposals, the conflict of the proposals with each other, their friends' preferences, and like it's a kind of relatively like simple heuristics for combining those things, but then we sort of push on the different parts and see like, okay, well, if we change how much they care about one thing versus another, how robust are the results? Because the nuts and bolts of these systems are that we literally don't know a lot of things. So we have to use this logic of signal processing, or like, you know, these sort of complex systems frameworks where you say, look, we don't know a bunch of stuff, but the system still provides a sort of shape of the world. And it's like saying, well, climbing a mountain is hard, no matter what, how much random energy you put into a bunch of particles, moving up the mountain is going to be less likely than, say, moving down it. And so I think a better way to think about these random processes is that we use both random processes and behavioral processes in lots of different combinations to try tests, and just try to see whether, despite all of those things, there are still some high-level predictable properties that we're planning for. And that's sort of robust in the sense that our results aren't contingent on a specific assumption, although not necessarily perfect no matter what. We can still run failure mode tests where we say, what if a person does the worst thing that we could possibly expect them to do? What happens? And the example I was giving about the sort of run on the bonding curve is an example of that. Like, we could just code the scenario where people sell and sell and sell, and what happens is eventually you sell down the curve, but you leave a bunch of money in the funding pool. So we can reason that that's probably not actually going to happen. Eventually it's going to go down far enough that someone's going to say, actually, it's worth it to me to not sell for this, you know, diminishing marginal return and stay here and guide those funds. And obviously this could fail iteratively in like chunk down, but it's actually still a protected failure mode. Yeah, okay, we never can build a system that can never fail, but we can build systems that have good catches to help prevent their failure modes.
Thanks so much. Thank you.
Cool.